This is FE Peer Review. The date is January the 23rd, 2024. Brian Leakey, star rotation map solution is Bogus. The Lambert azimuthal equal area projection. I got the idea to do this video because it fits in with my map projection series that I've been neglecting and have been wanting to get back to. So this is a good opportunity to do that. I also got the idea from Arctic Reflections. I'm sure you all know his channel. If you don't, please do go over and check it out. I'll put a link in the description. He does wonderful videos, very interesting stuff. And he put up a video just a few hours ago responding to, debunking a video put out by Brian Leakey that uses that particular map projection. So thank you, Arctic. I did leave Arctic a little note mentioning that I was going to be referring to his video here, and so I have done. Now let's take a quick step over to Brian's video. Brian put up a video where he took that map and then said that this map solves the problem of star rotation appearing to go in different directions north and south of the equator. I will include a link to his video in the description. I've noticed that his channel has suddenly got very, very few subscribers and very, very few views. So I thought that was kind of surprising. I don't know if he lost his channel and had to start fresh. Anyway, his channel is even smaller than mine. So I don't recommend encouraging him with too many comments and too many views and so forth. That just gets the algorithm all excited, and we know what happens with that. Anyhow, I did leave Brian a note to say, I see problems, I'll be doing a video response. And then I noticed another comment from Flat Earth Math, and I'm happy to say Flat Earth Math regularly watches my videos, and I appreciate his comments on my videos as well. He writes, interesting hypothesis, now do Orion. From the northern hemisphere, Orion appears to move counterclockwise around the north celestial pole near Polaris, yet at the same time, for viewers in the southern hemisphere, Orion appears to move clockwise around the south celestial pole. So where is Orion on your map and how does it move? Now that is a great debunk in just a simple question. It'll be fun watching Brian Leakey try to ignore that, because he's going to have to work hard at ignoring that. So as far as debunks go, it's already been done. I don't need to do it. Flat Earth Math has done it. Arctic Reflections has done it. I just wanted to take this opportunity to poke a little fun, but also more especially to get back to the Earth map projections. I tried to find Brian's specific image that he used for his video and could not find it through Google Images. It's the Lambert equal area azimuthal projection. And in this particular case, you'll see that it's centered on a spot in Africa. Now, I was able to find another image with the same exact projection from the same spot. We see that here. It says up above Lambert azimuthal equal area projection. And then down at the bottom, it says centered on the 15-degree east line of longitude. So the vertical axis of this circle is on the 15-degree east longitude line, and you can see that it's a bit to the east of Great Britain, to the east of Greenwich. And then the horizontal axis seems to be the equator. Doesn't actually say that here, but it appears to be the equator, the horizontal axis. So the center of this circle is 15 degrees east, longitude, 0 latitude. I've only mentioned that because the images we're going to be working with are slightly different than that. This is the one we're going to be looking at first, and this one, it's centered on 0, 0. The vertical axis and the horizontal axis are at 0, 0. So as you can see, the center of the circle is off in the ocean here. Johann Heinrich Lambert was a Swiss mathematician, and he produced this projection in 1772. He also did several other projections that have his name. This is the equal area. He also did an azimuthal equal distance, and then he also did a cylindrical projection. He may have done others I'm not aware of. Anyhow, it's quite a fun image. It in many ways is very useful depending on where you center it. You can put any point at your center and develop a projection from it. We're going to look at that, how the projection is actually worked out. By the way, the math for all of this can be found on a Wikipedia page. There's a wonderful Wikipedia page. Well, there are two of them I'll mention here. One is simply a list of map projections, and then it links to all these different projections. And right now I'm looking at the Lambert azimuthal equal area projection page, and it has the math if you want the math. The concept is this. Imagine that you're going to create your map on a tabletop here, and that's that line at the bottom. And you've got your globe. So you've set your globe on the table, and you pick the point that you want to center your map. So in the case of where we're looking at, that's 0 longitude, 0 latitude. But of course, you could pick any point. You could pick the poles. You could pick your hometown, whatever you'd like. Anyhow, once you set it on the table there, then you start rolling it. Well, in this case, we'll roll it to the right. And the spot that we see where I'm circling the mouse, where it touches the table, that marks the point on the map. And then we continue rolling it until the next point touches the table. And then the next touches the table. And finally, the opposite, polar opposite point there touches the perimeter of our map. Then recentering your map, you roll it the other way and you get the other half of that particular longitude line. Now, on that line of longitude, all your distances are going to be the same. Let's go back and take a look at it. So if we start at 0, 0 in the center, we will go north, following the 0 longitude line. And with each of these latitude marks, we see that the distance we've traveled scales the same. Let's scoot over to a different longitude line. I'm over here in the middle of South America, and I'm going to start at 0 and start at the equator and head northward. Along this longitude line, which is an arc, each of these lengths is equal. But these lengths are longer than these lengths. So you can see that the map is distorting the scale as it moves out towards the edge. So the distance between our longitude lines is getting more and more distorted as we move to the edge of the circle here. However, each of these areas defined to these. So there's one. And say here's another extreme. I'm not going to bother to try to draw the curves. I'm just marking the points so you can see it. Each of those areas is the same. That's why it's the equal area version of the azimuthal map. Now this is the Tissot's indicatrix, it's called, and it gives us a graphic representation of the amount of distortion we're seeing on the map, the amount of shape distortion. So 0, 0, the center of our map, this red circle represents no distortion. The extent to which that circle changes shape indicates the distortion. So if we go out the equator to the extreme, we see that the vertical axis is extremely elongated and the horizontal axis is shrunk, and that's just progressive all the way around. However, you do have a good chunk of the center of the map that's relatively undistorted. So since you can put any point you want, you can center it around wherever you want, you can at least get that part of our lovely globe without distortion. So that's the Lambert equal area azimuthal projection. I hope you enjoyed this. I thought it was kind of interesting and was also kind of amused that Brian is turning towards globe projections to try to find his flat Earth map, clearly without understanding the implications of what these projections hold. So Brian, take your map now that you've tried to work out the star paths on and which don't work for star paths, and check some of these distances. For example, the west coast versus the east coast of the United States. according to this map, the distance along the east coast is going to be shorter than the west coast. But when you actually measure it physically, you get different results. Good try though, Brian. Pat on the back. Keep on trying. And as far as the rest of you, I hope you enjoyed this. If you did, please give it a thumbs up. Subscribe if you haven't already. Do drop by Arctic Reflections channel if you haven't been there already. And I guess that's it. So have a great day.